We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.
Hello, greetings. This is Professor Jun Cahigal, and you might wonder why the 360-degree shift from astronomy to meteorology. Is there any relationship between astronomy and meteorology? Now, meteorology is the scientific study of the Earth's atmosphere that focuses on weather processes and forecasting. Now, those events are bound by the variables that exist in the Earth's atmosphere. So they include the following, such as temperature, pressure, water vapor, and the gradients and interactions of these variables and how they change in time. The majority of the Earth's observed weather is located in the troposphere. Now, my initial thought is that there is no relation, however, since astronomy includes our sun and moon. And I have revised that thought to say that meteorology depends heavily on astronomy. Like for example, the moon has an effect on the atmospheric pressure in much the same way as it affects the tides. This is not a huge impact on meteorology at all, but technically it does relate to meteorology. The sun, on the other hand, is where all the energy that drives the weather of the Earth. Any changes in the sun's activity will directly impact the weather and climate of the Earth. So it is important to have an understanding of astronomy since it has a significant influence on the weather. And by having an understanding of our weather and climate here on Earth, we can have a better understanding of the conditions of the atmospheres of some of the members of our solar system. So sit back and relax and learn about the elements that drives our weather and climate. So for this lesson, we will be dealing with a special branch of earth science known as meteorology. If you will recall, meteorology deals with the study of the conditions of the Earth's atmosphere. Now, in our previous lesson, we have studied the Earth's atmosphere and its layers. So we will now go into the details of those conditions that affect our atmosphere, and that includes weather and climate. And there are many factors that affect weather and climate, and two of those factors includes air pressure and winds. So in this lesson, we will be zooming in on air pressure and winds. Now we know from our previous lesson about the Earth's atmosphere that air pressure is equivalent to the weight of the air. So by definition, when we speak of air pressure is the pressure exerted by the weight of the air. And the weight of the air at sea level is about 1 kilogram per square centimeters, or that is equivalent to 14.7 pounds per square inch. Now, if you decide to climb a mountain, let's say if you decide to climb Mount Everest, then as you go higher, the air pressure decreases. So at sea level, the air pressure is 1 atmosphere, or that's 14.7 pounds per square inch. And as you go higher, the air pressure decreases. Now, it has something to do with the molecules of air. Now, air molecules, they are being pulled down by gravity. And as the air molecules are being pulled down by gravity near the surface of the Earth, the air near the surface becomes denser. And that is equivalent to a higher air pressure because of the denser air. So that guy near the base of the mountain, there are more atoms, there are more molecules pressing down on that guy. So that guy is experiencing higher air pressure as compared to the guy on top of the mountain. There are few air molecules pressing down on that guy. So that guy experiences lower air pressure. So again, let's take a look at these two guys. So the guy at the base of the mountain experiences higher air pressure because there are more air molecules pressing down on that guy near the base of the mountain. As compared to the guy on top of the mountain, there are less air molecules pressing down on that guy. So the guy on top of the mountain experiences lower air pressure. And in measuring air pressure, we need to consider the following units and instruments. So the unit for measuring air pressure is the millibar or MB. So a millibar equals 100 newtons per square meter, or the standard sea level pressure is 1013.25 millibars, or that's equivalent to 14.7 pounds per square inch. And there are instruments that are used to measure atmospheric pressure. So these are the following. First, we have the mercury barometer, where the height of the mercury column provides a measure of air pressure. The standard atmospheric pressure at sea level equals 29.92 inches of mercury, or that's about 760 millimeters of mercury. And we have the aneroid barometer. The aneroid barometer uses a partially evacuated metal chamber that changes shape as air pressure changes. Okay, so I want you now to take a look at this illustration of a mercurial barometer. The mercurial barometer was invented by an Italian by the name of Evangelista Torricelli. Now, in the mercurial barometer, you have a reservoir containing mercury. And as air presses down on the reservoir with mercury, it allows that column of mercury inside the tube to rise. And the standard height of that mercury inside the tube at sea level is 76 centimeters or 29.92 inches. So this is the mercurial barometer. And also we have the so-called aneroid barometer. The aneroid barometer contains an evacuated metal chamber that changes shape with changing air pressure. And as the evacuated metal chamber changes shape, it is translated into mechanical movement that will move those dials, those pointers that will indicate the changing air pressure. Now, the barometer, whether mercurial or aneroid, they play an important role in weather forecasting. So we will go to that later, the role of the barometer and air pressure in weather forecasting. Now, also we mentioned that as we increase in altitude, the air pressure also decreases. Now, everybody kindly take a look at this illustration. So we have three stations, Station A, Station B, and Station C. Now, Station A is at sea level, and the air pressure reading in Station A is 1008 millibars. Now, Station B has a height of 1000 meters, and everybody look at the air pressure on Station B. The air pressure at Station B is 915 millibars. And everybody look at Station C. Station C is 1,800 meters high. And the air pressure reading at Station C is 840 millibars. So the higher we go, the air pressure decreases. Now, there are times in some places that they would experience high pressure, and in some places they would experience low pressure. Now, these differences in air pressure will result in the movement of air, which we call as wind. So wind is the result of these horizontal differences in air pressure, and air or wind moves from regions of high pressure to regions of low pressure. Air or wind moves from areas of high pressure to areas of low pressure. Now, to illustrate the movement of the air as a result of the differences in air pressure, I want you now to take a look at this diagram. Now, the heat from the sun also plays an important role in this general movement of air. Now, everybody look at the diagram. So, as the sun heats up the air molecules begins to move. There is increase in the kinetic movement of molecules. And as a result, the air becomes less dense as it is heated. And as the air becomes less dense, heated air rises, creating an area of low pressure. Low pressure because the air is lighter because it is less dense. Now, as the air cools off, there is decrease in the kinetic movement of molecules. So the air becomes denser, the air becomes heavier, and as a result, this creates a region of high pressure. So that is the general circulation of air. Air moves from a region of high pressure to a region of low pressure. And that's how winds are produced. Winds are produced as a result of this difference in air pressure. Air moves from a region of high pressure to a region of low pressure. Now, to further illustrate this movement of air as a result of the differences in air pressure, let's take a look at this diagram. Now again, the sun plays an important role in this movement of air. Now, as the sun heats up the air molecules begins to move. There is an increase in the kinetic movement of molecules. And as a result, the air expands when it is heated. And as the air expands, it becomes lighter. And this heated air, because it is lighter, begins to rise, creating an area of low pressure. Now, as the heated air cools off, there is a decrease in the kinetic movement of molecules. So the air becomes denser, the air becomes heavier, and this cold air sinks, creating a region of high pressure. So this difference in pressure will result in a general movement of air from a region of high pressure to a region of low pressure. So that's how winds are produced. Winds are produced because of this difference in pressure. So heated air rises, creating a low pressure area, and cold air sinks, creating a region of high pressure. So this difference in pressure will result in the general circulation of air from high pressure to low pressure, creating winds. So as you could see, the sun really drives our weather. As the sun heats up the air, the heated air expands, producing an area of low pressure because the heated air rises, and cold air sinks, creating a region of high pressure. So always take note that as heated air rises, it carries a lot of moisture. And this moisture will result in the formation of clouds. Clouds would bring rain. So we usually associate low pressure with cloud formation and rain. A low pressure area is always associated with bad weather. Now, cold air sinks, creating a region of high pressure. Now, cold air contains very little moisture, so there's no cloud formation. So, no clouds means no rain, no precipitation. So, a high pressure area is usually associated with dry air, and that means fair and good weather. So now you know the relationship between high pressure and low pressure and whether we would get bad or fair weather. So let's take a look at this diagram. So as heated air rises, this heated air packs a lot of moisture. And this moisture will trigger the formation of clouds. Clouds would bring rain. So a low pressure area is always associated with wet, cloudy, and rainy weather condition. Okay, now for cold air, we know that cold air is denser, cold air is heavier, so cold air sinks or cold air descends. This will create a region of high pressure. Now, cold air contains very little moisture. So if there's little moisture, that means there's little chance for clouds to form. So if there are no clouds, there's no precipitation. So a high pressure area is always equated with dry, bright, sunny, and fair weather. So isn't that fascinating about winds? Alright, now to summarize the production or the creation of winds. So take note that winds are created by, number one, heating the air. So as a result of heated air rising, there is a decrease in atmospheric pressure. Warm air rises, creating a low pressure area. Now cool air rushes into replacing the warm air. Cold air is denser, and this creates a high pressure area. And because of this difference in pressure, air moves from a region of high pressure to a region of low pressure. And as a result, air moves and winds form. Okay, so now you know how winds are created. Okay, so let's talk about now pressure gradient and pressure maps. Now, the pressure gradient force is the primary driving force of wind as a result from pressure changes that occur over a given distance as depicted by the spacing of isobars. These are lines drawn on a weather map that connects places of equal air pressure. And the spacing of these isobars indicate the amount of pressure change occurring over a given distance, expressed as a pressure difference or a pressure gradient. Okay, everybody kindly take a look at this weather map. So those lines are isobars. These isobars, they indicate areas of equal pressure. So by just looking at these isobars and knowing the pressure differences, we can now determine how much pressure changes that occur in a given area. Okay, so I hope everything is clear about air pressure, and differences in air pressure will produce winds. Alright, let's talk about now the so-called Coriolis effect. Now remember, as we mentioned a while ago, that air moves from a region of high pressure to a region of low pressure. Now, if we would think that at the global scale, there is high pressure at the polar regions and there is low pressure at the equator, because the air at the equator is heated, so the heated air rises, producing a low pressure area. Now at the polar regions, you have cold air, so cold air sinks, creating a region of high pressure. So in a general circulation at the global scale, air moves from poles to the equator. But remember, our Earth is rotating. So air is somewhat deviated, or the air is deflected. Now this deflection due to the rotation of the Earth is known as the Coriolis effect. Now the Coriolis force produces a deviation in the path of the wind, and this is due to the Earth's rotation. Now to the right, the air is deflected in the northern hemisphere, and air is deflected to the left in the southern hemisphere. Now to further explain the Coriolis effect, let's take a look at this diagram. So in a non-rotating Earth model, generally air moves from poles to equator. Now the equator is an area of low pressure because the sun heats up the air at the equator. Heated air rises, producing a low pressure area. Now at the poles, air is cold and cold air sinks, producing a high pressure area. Now, this difference in pressure will produce a general movement of air from poles to equator. But always remember that our planet Earth, is rotating. So, the winds will be deflected by this rotation of the Earth. So, this deflection of the wind due to the rotation of the Earth is known as the Coriolis effect. Now, at the northern hemisphere, the air is deflected to the right, and in the southern hemisphere, the air is deflected to the left. Now, that's really fascinating about the Coriolis effect. Now, because the Earth is rotating, the winds in the northern hemisphere, they are deflected to the right, and the winds in the southern hemisphere are deflected to the left. So that's the Coriolis effect. The Coriolis effect is the deflection of the winds due to the rotation of the Earth. So in the northern hemisphere, the air is deflected to the right, and in the southern hemisphere, the air is deflected to the left. So for this lesson, we will have a review of the Coriolis effect. Plus, we will study the so-called global wind system. Plus, we have monsoon winds. And we will study local wind systems. So that includes sea breeze and land breeze. So before we move on, let's have a quick review of our previous lesson. Now, we all know for a fact that differences in air pressure is caused by the unequal heating of the Earth's surface. So we know for a fact that the equator receives more heat from the sun than the polar regions. So the air above the equator is heated more, causing the air to become less dense. And when the air becomes less dense, the air becomes lighter, so heated air rises, creating a low pressure area. And we know for a fact that as the air is heated, it brings a lot of moisture. And this will trigger the formation of clouds and precipitation. So an area of low pressure is always equated with stormy weather. Now, at the poles, we have cold air. Now, cold air is denser, so cold air sinks, creating an area of high pressure. And cold air brings little moisture. So, this region of high pressure is always associated with clear, good, fair weather. Now, this difference in pressure, high pressure and low pressure, will cause air to move. And this is what we call winds. Okay, so everybody, I want you now to take a look at this diagram. So there are places wherein the earth receives more heat from the sun, like the equator. And at the poles, the earth receives little heat. So as the equator is heated, the heated air becomes less dense. So this heated air rises, and this will create an area of low pressure. And as the air is heated, it brings a lot of moisture. So this moisture will trigger the formation of clouds. Clouds would bring rain. That is why an area of low pressure is always associated with stormy, bad weather. Now at the poles, the air is cold, and cold air is more dense, or the air is heavier. So cold air sinks, creating an area of high pressure. And cold air brings very little moisture. So that means there's little chance for clouds to form. So a high pressure area is always associated with fair and good weather. And this difference in pressure will cause the air to move from a region of high pressure to a region of low pressure. So this movement of air is what we call as wind. So to further illustrate this movement of air or wind due to differences in air pressure, let's take a look at this diagram of the circulation of air inside a room. Alright, so can you see that radiator at one corner of the room? So that radiator heats up the air. The heated air becomes less dense, so that heated air rises, so it creates an area of low pressure at that corner of the room. And as the warm air rises, it nears that window at the other corner of the room. So eventually the air cools and it becomes more dense, or it becomes heavier, so that cool air sinks And at that corner of the room near the window, that creates an area of high pressure. So, the movement now of air inside the room would be from a region of high pressure, which is near the window, to an area of low pressure near the radiator. So that's the general movement of air inside the room from high pressure to low pressure. And that's what we call a convection cell. Now that is really fascinating about the general circulation of air inside a room. Plus also we know from the previous lesson that the passage of a low pressure area is usually associated with unstable conditions and stormy weather, because we know that heated air packs a lot of moisture. As the air rises, it creates a low pressure area, and that heated air contains a lot of moisture that may trigger the formation of clouds and precipitation or rain. Now, on the other hand, fair weather can usually be expected with the approach of a high pressure system. So a high pressure area is always associated with good fair weather, because we know that cold air contains very little moisture, so there is little chance for clouds to form. So an area of high pressure is always associated with fair and good weather condition. Now let's take a look at the general circulation of air on a global scale. Alright, so everybody kindly take a look at this illustration of the Earth with the general circulation of the air. Alright, so we know that the equator receives more heat from the sun than the polar regions. So at the equator, heated air rises, and that creates an area of low pressure. So along the equator, there is low pressure. Then cold air sinks at the polar regions. So the polar regions, those are areas of high pressure. So the general circulation of air on a global scale would be from polar regions to equator. Alright? That is the scenario if the Earth is not rotating. But the Earth is rotating, so what happens to the movement of air is that the air or the winds are deflected. Okay? And this is what we call as the Coriolis effect. The Coriolis effect is the deflection of the winds due to the Earth's rotation. Now, in the northern hemisphere, the winds are deflected to the right, and in the southern hemisphere, the winds are deflected to the left. So that is the effect of the rotation of the Earth on the movement of the air or winds. That in the northern hemisphere, due to the Earth's rotation, the winds are deflected to the right, and in the southern hemisphere, the winds are deflected to the left. And the amount of deflection is greater at 60 degrees latitude than at 40 degrees latitude, which is greater than at 20 degrees latitude. And furthermore, there is no deflection observed for the airflow along the equator. So everybody kindly take a look at this illustration of the Earth showing the deflection of the winds. Okay, so there is largest deflection at 60 degrees latitude compared to 40 degrees latitude. There is least deflection at 20 degrees latitude, and there is no deflection at the equator. Now that is really fascinating about the amount of deflection due to the Coriolis effect. Alright, so let us now differentiate between cyclones and anticyclones. Now we usually associate cyclones with typhoons. Now here in the Philippines, we call them typhoons, And in the United States, they call them hurricanes. Now, what are cyclones anyway? Now, cyclones, these are centers of low pressure. So you know what that means when you say low pressure, that is associated with stormy, bad weather. And the spin or the circulation of air of a cyclone is counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Okay, everybody, kindly take a look at this satellite photo of a cyclone at different locations. So in the northern hemisphere, you will notice that the cyclone spins in a counterclockwise direction. And in the southern hemisphere, a cyclone spins in a clockwise direction. Now, the spinning motion of a cyclone is due to the Coriolis effect. Now, everybody kindly take a look at this satellite photo of a typhoon inside the Philippine area of responsibility. So you will notice that the typhoon spins in a counterclockwise direction since the Philippines is in the northern hemisphere. Okay. Alright, everybody, take a look at this. So this is the United States, and in this weather map, there is a cyclone. So since the United States is in the northern hemisphere, that cyclone spins in a counterclockwise direction. Okay, so cyclones in the northern hemisphere, they spin in a counterclockwise direction. Cyclones are low pressure centers, so they bring stormy, bad weather. Alright, here is a satellite photo of Australia. So you will notice that the cyclone spins in a clockwise direction since Australia is in the southern hemisphere. Now, that is really fascinating about cyclones. Cyclones, these are low pressure centers. Here in the Philippines, we call them typhoons. And a cyclone spins counterclockwise in the northern hemisphere, like here in the Philippines. Typhoons, they spin in a counterclockwise direction. And cyclones, they spin clockwise in the southern hemisphere. Now, what about anticyclones? Now, anticyclones, these are areas of high pressure. And you know what that means. When you say high pressure, we associate high pressure with fair, clear, and good weather. Now, the airflow of an anticyclone is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So, anticyclones are areas of high pressure. So, they bring clear, fair, good weather. And in the northern hemisphere, the anticyclone spins in a clockwise direction. Okay, everybody take a look at this diagram. So here is a high pressure center in the northern hemisphere. So this anticyclone spins in a clockwise direction in the northern hemisphere, but in the southern hemisphere, this anticyclone will spin in a counterclockwise direction. Okay, and just like cyclones, anticyclones, they spin because of the Coriolis effect. Now, everybody, kindly take a look at this animated diagram. So, anticyclones, these are areas of high pressure. And high pressure areas are caused by sinking cold air. So, cold air is denser, so cold air sinks, creating regions of high pressure. And cold air brings little moisture, so there's little chance for clouds to form. So a high pressure area is associated with good, fair weather. This is in contrast to cyclones. Cyclones, these are areas of low pressure, and this is caused by rising warm air. Rising warm air packs a lot of moisture, so that would trigger the formation of clouds and precipitation. So that's how we differentiate between cyclones and anticyclones. And we measure air pressure using an instrument called a barometer. Now, there are two types of barometers. You have the mercurial barometer that uses a column of mercury, and we have the aneroid barometer that contains an evacuated metal chamber that changes with changing air pressure. Right now, for wind measurements, we consider the following. There are two basic wind measurements. We have direction and speed. So for wind direction, we make use of the wind vane. Wind direction is commonly determined using a wind vane. And for wind speed is often measured using a cup anemometer. Alright, so here is an illustration of these two instruments. So on top, we have a wind vane. The wind vane measures wind direction. And that rotating thing is the cup anemometer. The cup anemometer measures wind speed. Okay, here is a cup anemometer that measures wind speed. Now, these weather instruments, the barometer, the anemometer, and the wind vane, they play important roles in weather forecasting. Now, this global movement of air acts like a giant heat transfer system. This moves warm air towards high latitudes and cool air towards the equator. So in a way, the temperature of the earth is somewhat regulated by this movement of air. Now, this heat transfer system plays an important role in distributing heat globally. So this system moves warm air towards the high latitudes and cold air towards the equator. So in a way, this giant heat transfer system regulates global temperature and thus maintaining life on Earth. Okay, now let's imagine that the Earth is not rotating. So in a non-rotating Earth, there would be two giant convection cells that would form. So there is one giant convection cell in the northern hemisphere and another convection cell in the southern hemisphere. So everybody, I want you now to take a look at this illustration. So in a non-rotating Earth, there would be two giant convection cells that would form. Alright, everybody, focus on this illustration. So along the equator, air is heated. And as air is heated, air rises, producing a low pressure. So along the equator, you have a low pressure area. Then cold air sinks at the poles. So cold air sinks, creating a high pressure area. And we know that air moves from a region of high pressure to a region of low pressure. So air moves from poles to equator. So as you can see, there are two giant convection cells. So one at the northern hemisphere and one in the southern hemisphere. But the Earth is rotating. Okay, and because the Earth is rotating, the air is somewhat deflected. So what happens here is that the rotation of the Earth would break down the two convection cells into smaller cells. That's why we have now what we call our global wind system. Now again, because the Earth is rotating, these two giant convection cells would be broken down into smaller convection cells. And this would represent our global wind system. So here's a diagram showing the global wind system. So let's start now with this global wind system starting at 0 degrees latitude, that's the equator, up to 30 degrees north latitude and 30 degrees south latitude. And that particular wind system is what we call as the trade winds or the tropical easterlies. Now, the trade winds, these are winds that reliably blow from east to west. That is from 0 degrees latitude, that's the equator, up to 30 degrees north latitude and 30 degrees south latitude. Okay, so that's what we call the trade winds or the tropical easterlies. So from 0 degrees, that's the equator, up to 30 degrees north latitude and 30 degrees south latitude. And the winds blow from east to west. Okay, and sailors have been using the trade winds for centuries. Sailors traveling from Europe or Africa use the trade winds to travel to North or South America. Now let's focus our attention on the equator. Now winds from the north and winds from the south, they all converge at the equator. And we know that the equator is an area of low pressure because the sun heats up the equator more than the poles. So heated air rises vertically at the equator. So as a result, there are no winds in this area at the equator. So this becomes an area of calm. Okay, so this area at the equator is what we call as the doldrums. So right at the equator, there is almost no wind at all. So this area sometimes is called the doldrums. So walang hangin dito sa doldrums. So if you are sailing and your boat has no power, no engine, you might get stranded in the doldrums kasi wala pong hangin dyan. Okay, and many sailors through the centuries, sometimes they get stuck in the doldrum for weeks kasi wala pong hangin dyan. So that's quite fascinating indeed. So let's say you are in a sailboat and your sailboat has no engine, no power, then you might get stuck in the doldrums because the doldrums is an area of calm. There's literally no wind in the doldrums. Okay, so let us now focus on this wind system starting at 30 degrees north latitude to 60 degrees north latitude and 30 degrees south latitude to 60 degrees south latitude. So this wind system is what we call as the westerly winds or the prevailing westerlies. So these are prevailing winds from the west towards the east in the middle latitudes between 30 degrees and 60 degrees latitude, that's north and south. So the westerly winds, if you will take a look at this diagram, the westerly winds are located at about 30 degrees to 60 degrees north latitude and 30 degrees to 6 degrees south latitude. And you will notice that the winds, they move from west to east, which is the opposite of the trade winds or the tropical easterlies. Okay, so that's the westerly winds or the prevailing westerly. So the winds, they move from west to east, which is opposite of the trade winds. And lastly, we have what we call the polar easterly winds. Now, the polar easterly winds, they are located 60 to 90 degrees north latitude and 60 degrees to 90 degrees south latitude. So that wind system are the polar easterly winds. The polar easterlies are dry, cold, prevailing winds that blow from the high pressure areas of the polar highs at the north and south poles towards the low pressure areas within the westerlies at high latitudes. This particular belt of wind begins at approximately 60 degrees north and south latitude until they reach to the poles at about 90 degrees. So let's take a look at this diagram. So the polar easterlies, they are located 60 to 90 degrees north latitude and 60 to 90 degrees south latitude. And you will notice that the winds, they move from east to west, which is similar to the tropical easterlies. Now, I hope everything is clear about our global wind system. Okay, let's talk about now monsoon winds. Now, when we speak of monsoon winds are the seasonal reversal of wind direction. And this is usually associated with large continents, especially Asia, and that includes the Philippines. Now, here in our country, we experience two monsoon wind system. So we have the southwest monsoon, also known as hanging habagat. Usually it begins in June and ends in September, but it may extend up to late October. And we have the northeast monsoon or hanging amihan, usually begins in late October and it may even extend up to January. Now, let's talk about the northeast monsoon or the so-called hanging amihan. Now, during the months from October to January, and it may even extend up to February, there is a high pressure area over Siberia. And you know what that means if there is a high pressure area? So there is cold air. Cold air sinks, creating this high pressure area over Siberia. And cold air brings little moisture. So, during the months from October up to February, our country experiences clear, fair, and cold weather. That's why during the Amihan season, ramdam na natin ang Pasko because of that cold air over Siberia. So pagdating ng October, November, December, January, ramdam na po natin ang Pasko because of the hanging amihan or the northeast monsoon. Now, what about the so-called southwest monsoon? Now, during the southwest monsoon season, there is a low pressure over northern India. And you know what that means. If there is a low pressure area, so you have heated air, and that heated air rises, bringing a lot of moisture. Okay? And during the southwest monsoon, because of the moisture content of the air, the southwest monsoon brings torrential rains and flooding, especially here in the Philippines. So during the so-called hanging habagat season, this is the so-called rainy and stormy season here in the Philippines. So dito po sa atin sa Pilipinas, pag hanging habagat, we expect more storms and torrential rains during the months of June to September, and it may even extend up to late October. So that's the so-called hanging habagat or the southwest monsoon. So to summarize this lesson on monsoon winds, so during the months of June to late October, we usually experience stormy and rainy months. That's from June to October. Again, that is due to the southwest monsoon or the hanging habagat. So we experience flooding, torrential rains, typhoons during the months of June to late October. Then during the months of November to February, that's the so-called hanging amihan season or the northeast monsoon. So the northeast monsoon brings cold air from Siberia. So we experience clear, good, and cold weather. Okay. And from March to May, that's the transition period. So we experience the easterly winds. So that brings summer and hot weather during the months of March to May. Alright, so that's how we experience our weather here in the Philippines. So I hope everything is clear about monsoon winds. Now, after studying our global wind system, let us now proceed to a detailed look of our local wind system. Now, when we speak of local wind systems, these are winds that blow over a limited area. Local winds blow between small, low, and high pressure systems, and they are influenced by local geography, such as nearness to an ocean or a lake or a mountain range that can affect local winds. Now, examples of local wind systems includes sea breeze, land breeze, valley breeze, and mountain breeze. Okay, let us now zoom in first on sea and land breeze. Now, in coastal areas during the warm summer months, the land surface is heated more intensely during the daylight hours than the adjacent body of water. And as a result, the air above the land surface heats, expands, and rises, creating an area of low pressure. Now, during nighttime, the reverse takes place. Now, to further illustrate that, everybody, I want you to zoom in on this illustration. So, if you will notice, this is during daytime, so the land heats up faster than the adjacent body of water. So the air over the land expands, and eventually this heated air rises, creating an area of low pressure. Then the body of water, the air is cooled, so cold air sinks, and this creates an area of higher pressure. So since there is a difference in pressure, the air moves from high pressure to low pressure, or that means from sea to land. Okay? And this is what we call a sea breeze. Now that's really fascinating about sea breeze. So again, sea breeze occurs during daytime. So during daytime, the land heats up faster than the adjacent body of water. So the air over the land expands and the heated air rises, creating an area of low pressure. Then the air above the water is cold, so cold air sinks, creating an area of higher pressure. So this difference in pressure will allow air to move from sea to land. So that's what we call a sea breeze. Now the opposite occurs during nighttime. Okay, during nighttime, the land cools quickly than the adjacent body of water. So the air over the water heats up and expands, so that heated air above the water rises, creating now an area of low pressure over the body of water. Then the cold air over the land sinks, so that creates an area of higher pressure above the land. Okay, so there is now a shift. So since there is now a difference in pressure, the air moves from higher to lower pressure, or from land to sea. And this is what we call a land breeze. Now, aside from sea breeze and land breeze, other examples of local wind systems includes valley breeze and mountain breeze. Okay, let's take a look at valley breeze and mountain breeze. Now, during daytime, the air along the slopes of the mountains is heated more intensely than the air at the same elevation over the valley floor. Now, because this warmer air on the mountain slopes is less dense, it glides up along the slopes and generates a valley breeze. Now, during nighttime, the pattern may reverse. Okay, so everybody, kindly take a look at this illustration. Now, during daytime, the air over the slopes of the mountains, they are heated more than the air above the valley floor. So that means that the air over the slopes of the mountains, they rise and creates a low pressure area. Then along the valley floor, the air is cold, so cold air sinks, creating an area of higher pressure. So that means that the air moves from higher pressure to lower pressure. So as you could see, using the arrows in our illustration, the air moves from valley floor, then the air slides along the slopes of the mountain. So you will be experiencing what we call a valley breeze. Now, the reverse occurs during nighttime. So during nighttime, the air above the mountain slopes, they cool quickly as compared to the air above the valley floor. So the air along the slopes of the mountain, the cold air sinks, creating an area of high pressure. Then the heated air above the valley floor rises, creating an area of lower pressure. So this difference in air pressure will cause the air to move from mountain slopes to valley floor. So the high pressure in valley causes the winds to flow downward. And this is what we call a mountain breeze. Now that's really fascinating about mountain breeze and valley breeze. So there are local wind systems along those regions, along mountainous areas and valleys. Now let's take a look at this illustration explaining again the movement of air along those areas. So during daytime, the air above the mountain slopes, they are heated. So the heated air rises, creating an area of low pressure. Now the air above the valley floor is cold, so cold air sinks. And that creates an area of higher pressure. So the air moves from high pressure to low pressure. So that means the air moves upwards. And that's what we call a valley breeze. Now, the reverse happens during nighttime. So during nighttime, the air above the mountain slopes, they cool quickly. So cold air sinks, creating an area of high pressure as compared to the air above the valley floor. So the air moves from high pressure to low pressure. So the air moves downwards during nighttime. And that's what we call a mountain breeze. Okay, so I hope everything is clear about mountain breeze and valley breeze. Alright, so let us now study the so-called El Nino and La Nina weather phenomena. Now, what is this El Nino weather phenomena? Now, El Nino is the name given to the periodic warming of the ocean that occurs in the central and eastern Pacific Ocean. So that includes some countries in South America. And at irregular intervals of 3 to 7 years, these warm countercurrents become unusually strong and replace normally cold offshore waters with warm equatorial waters. And this El Nino episode can cause extreme weather in many parts of the world. Now, to further explain what happens during an El Nino episode, let's take a look at this illustration. So, during an El Nino event, there is an increase in the temperature of the waters in the eastern Pacific Ocean. So, that includes the waters in some countries near South America. So, these warm waters would heat up the air above it, and that heated air rises, carrying with it a lot of moisture. And this moist, warm air would trigger the formation of clouds. So during an El Nino episode, there would be torrential rains and flooding in some countries in South America. Now, the opposite occurs in the western Pacific Ocean, wherein the air is dry. So in countries like the Philippines, Indonesia, Australia, during an El Nino event, there would be extreme drought and dryness. So that's what happens during an El Nino episode. Now that is really fascinating about the El Nino phenomena. Now again, during an El Nino event, there is a shift in the temperature of the waters in the eastern Pacific Ocean. The waters in the eastern Pacific Ocean would increase, and these warm waters would heat up the air above it, and that heated air rises, bringing with it a lot of moisture. And this moist, warm air would trigger the formation of clouds, and clouds would bring rain. So in some countries in South America, during an El Nino event, they would experience torrential rainfall and extreme flooding. Now, the opposite occurs in the western Pacific Ocean, wherein the air is dry. So this includes countries like some parts of Australia, Indonesia, and the Philippines. So during an El Nino event, in these countries, they would experience extreme dryness and drought. Okay, and that's really interesting indeed during an El Nino event because of this shift in the temperature of the waters. So in the eastern Pacific Ocean, there is an increase in the temperature of the waters during an El Nino event. So an El Nino event would really affect the weather systems of many parts of the world, again because of this shift in the temperature of the waters in the Pacific Ocean. So during an El Nino event, there is an increase in the temperature of the waters near South America. So this heated water would bring moisture, then that moisture would trigger the formation of clouds and torrential rains in some parts of South America and even in California. And in the opposite part of the world, in the western Pacific Ocean, countries like the Philippines, Indonesia, and some parts of Australia would experience extreme drought and dryness. So that is the El Nino phenomena. Now, what about the La Nina weather phenomena? Now, La Nina is a climate pattern that describes the cooling of the surface ocean waters along the tropical west coast of South America. So this time, during a La Nina event, the surface temperature of the waters in South America would decrease, and there is an increase in the surface temperatures of the waters in the western Pacific Ocean, and that includes the Philippines, Indonesia, and some parts of Australia. So the La Nina is considered to be the counterpart of the El Nino phenomena, which is characterized by unusually warm ocean temperatures in the equatorial regions of the Pacific Ocean, especially in the western part of the Pacific Ocean, and that includes countries like Australia, Indonesia, and most especially the Philippines. So to further explain what happens during a La Nina event, let's take a look at this illustration. So during a La Nina event, there is a shift in the temperature of the waters in the Pacific Ocean. This time, there is warming of the surface waters in the western Pacific Ocean. So the warm waters in the western Pacific Ocean, that includes the Philippines, Indonesia, and some parts of Australia, to heat up, and this heated air rises, bringing with it a lot of moisture. And this moist air would trigger the formation of clouds, and clouds would bring torrential rainfall and flooding in those countries like the Philippines, Indonesia, and some parts of Australia. Okay, so that's what happens during a La Nina event. So during a La Nina event, again, there is a shift in the surface temperature of the waters. There is an increase in the temperature of the waters in the western Pacific Ocean. So that would heat up the air above it. Heated air rises, bringing with it moisture, would trigger the formation of clouds and torrential rainfall and flooding in countries like the Philippines, Indonesia, and some parts of Australia. So that's what happens during a La Nina event. Well, I guess that's about it tonight. I hope you have learned a lot about the basic concepts of weather and climate. And I hope you would realize also the relationship between astronomy and meteorology. Now again, the moon, the sun, they greatly influence our weather system. So in a way, astronomy and meteorology are somewhat connected or related. Okay, so I would like to thank the officers and crew of the BEDAN Society of Young Astronomers. And I would like to thank also the administrators of San Beda University Senior High School for their continued support of our organization. So always check out our Facebook page for updates. That is the BEDAN Society of Young Astronomers. And also check out our Twitter account. Alright, so this is Professor June Cahigal saying, live long and prosper, and I will see you soon. Okay, stay safe everybody, and good night.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.